Yeah, so I think we can start today's session. So, for your information, the recording has begun. So, yeah, once again, hello to the attendees. I am Jyotishwaran, a PhD student from the ECE department of IIT Roorkee. And this is the weekly discussion session for the Physics of Nanoscale Devices NPTEL course. Uh, Today we shall be covering the contents that were covered in week 3 of your course. So, yeah. Can you guys see the slides?
Yes, sir.
Yeah, okay. So, again, we shall follow a pattern similar to last week, where I'll briefly go through the topics that. Oh, sorry, I closed it by mistake. Uh, yes. So, yeah, I shall go through the topics that have been covered. But yeah, before that, to the two people attending, uh, do you guys have any doubts from the previous weeks?
Hello, sir.
Yeah.
Uh, from week two, actually, I go through that
Mm-hmm.
electron in 1D solid. So where
Yes.
number of electrons are there in that solid, and with the help of chronic Penny model and Bloch's theorem,
Mm-hmm.
and also with the help of Schrodinger equations, we calculated the
Yes.
wave function.
Yeah.
So, sir, after solving all the derivation, we had some constant values like A, B, C, D parameters.
Yes.
So in that, sir, that all those value are almost constant. So
Mm-hmm.
for that calculation, we generally take boundary conditions
Yes.
and solve that. So, sir, last equation we got, sir, show the last equation. But after
Yes.
then, one waveform he drawn like EK relationship, the
Yes.
EK diagram. So,
Yes.
sir, the question is that from that equation, how we draw that
Okay,
waveform?
okay, okay, okay. Okay, in that case, I think we can start today's discussion with that itself.
Yes, sir.
And, then we can move on to, because week 3, actually, the number of topics covered is actually not that much. So we can,
Mhm.
whatever I have planned, we can cover rather quickly. So yeah, let us revisit the KP model, because yeah, last week, since we had to do both week 1 and 2, most of our session was
Right, sir.
occupied in just doing the quantum mechanics and the reciprocal spaces. So yeah, let us spend some time with the chronic penny model to start today's session. So for reference, let me just 1 second. Uh, yeah, so for reference, let me share the screen. Yes, so yeah, hello, Mr. Satimurthy. Welcome to the session. Uh, so yeah, let us go through the slides themselves. So you can see my browser window, right?
Yes, sir.
Yeah. So let me increase the zoom. Yeah, perfect. So, so I suppose this is the graph that you're asking about, or is it this one? Kamal, can you confirm?
Top one, sir. Top one.
Top one.
Top one, sir.
Okay, okay, okay. Wonderful. So I suppose you're okay up until this point, correct?
Yes, sir.
This equation, until this equation, I suppose you have been able to follow.
No.
Yes?
Yeah, actually, I told that this equation comes from some regress derivation. Then
Yes.
after then
Ah,
we have
okay.
to draw this.
So yeah, so essentially the derivation is just following these applying these four boundary conditions, and then kind of taking some
Yes, sir.
assumptions on the potential and doing some change of variables. Okay, so that you will
Okay, sir.
actually
Okay.
find in any standard solid state physics textbook like Charles Kittle or Ashcroft and Mermin or books like this should have that. But for the purpose of our course, this material again, as I told you before, you just need to understand the ideas of quantum mechanics. You need not know like the entire details of these things because that will take too much time and effort, and it is not directly relevant to the course. Okay, so
Understand.
right now,
Understand.
yeah, we have this equation. Okay, so on the right hand side, you will see that there is a cos k of a plus b, and on the left hand side, you
Hmm.
have an equation that is entirely in the variable xi, where xi is
Okay, sir.
defined as E by u naught. So E by U naught is essentially an scaled energy parameter. Like E is the energy of the particle and U naught is like the height of the potential well. So E by U naught kind of tells me how large my energy is with respect to the potential well depth. Is that clear?
Yes, sir.
Okay. So remember last week's discussion. What does the variable K signify?
He also told like this K is
No,
different
like
from that initial K.
no, I mean, our discussion last week. You can use that.
Okay. Okay. Wave number, sir.
Yes, it is a wave number, and what does the K particularly signify? It is a state identifier, it is a marker. Each K value corresponds to an electron state. Correct?
Okay, sir.
Do you remember,
Hmm.
like when we solved the particle in a box, like finally, when I will open that whiteboard also. So going back, I have those things here. So, yeah, let this thing open up. So, if you remember, over here, each
Okay. Okay.
of
Okay. Okay.
these
Last.
k
Last.
values corresponded to
Right.
an energy state in the 1D box. Correct?
Mm-hmm.
Like this is a wave
Right.
function
Right. The
for
issue
what? K equal
happened.
to 3 pi by
Yes, sir.
a. So similarly, for k equal to pi by
Hmm.
a, there would have been a wave function. For k equal to 2 pi by a, there would have been a wave function. For 4 pi by a, there would have been a wave function. So we listed like all possible values. Similarly, the negative values are also defined, but we in our discussion saw that plus and minus values of the same k represent the same state. So this was also discussed based on the quantization of momentum and quantization of p square and things like that. Like this was kind of a off tangent discussion, but we spent a lot of time on this. So I hope you can recall this. You can also revisit like the video and the slides of last week's discussion should be shared with you
Yes,
by
sir.
now.
Actually, while going through your lectures, means sir's lecture, na?
Hmm. Yes.
Hello.
Yeah. Hello. Can you hear me? Hello. Am I audible?
Yes, sir.
Yeah. Yeah.
Yes,
So what
sir.
were you saying? Yeah.
Yeah. Actually, last time you told this everything, na. So while
Yes.
going through the third lectures, na, actually I can't correlate this lecture with that
Okay, okay, okay. Yeah,
because of
that happens. It
right.
takes some getting used to. But yeah, unfortunately, since the whole thing is happening online, it is an unfortunate shortcoming, because ideally speaking, how this would have happened is, if this were a classroom course, then Professor Vishwant would have taken a class, and there would have been tutorial sessions where I would have been covering these concepts. So it would have happened at the same time.
Yeah, yeah.
So, but since there is, kind of a time lag, you should have access to the recordings of last week's session. So whenever you want to go back to those things, feel free to go back and, revise whatever we have discussed. And for the
Yes,
most
sir. Yes,
part,
sir.
yeah, does someone else have a question? Hello. I heard another voice briefly.
No, sir, no question.
No questions. Okay, okay. Yeah. So, yeah, moving on. So, that is the thing. So, whenever I write the K value, each K value corresponds to an electronic energy state. Okay. So, that is what we are looking at when we consider this equation. So, the K on the right hand side says that there is, like, for, so essentially over here in this equation I'm solving for K. Okay, so the equation, my procedure for solving is to find values of K. So as you can see, now how do we go about solving this equation? As you can see, this equation is like very complicated. So there is no straightforward method like we use for solving linear equations or, quadratic equations. There is no explicit formula that will tell us what the values of K will be. However, we can solve this graphically, because whenever, we have such complicated equations, we typically either use numerical methods or, we try to solve them graphically. So to solve this equation graphically, what we first do is we plot the function that is on the left hand side. So that is this curve that you see here. This oscillating curve that you see here,
Hello,
that
sir.
is, yeah.
Sir, actually, slide is not visible right now.
Oh, it's not visible. Oh, okay. So please,
Yes.
oh, okay.
Yeah.
Yeah, Google has seen fit to stop my presentation. Uh, Apologies. Yeah,
No
whenever you
need.
have such issues, please, like, immediately bring it to my notice. Yeah, so I hope you can see it now.
Yes, sir.
Yeah. So, as I was saying before, let me repeat. The aim of solving like this equation is we are solving for K. Like the solution from this equation are the values of K, because the values of K will allow me to identify the electronic energy states. Okay. So finding K is the aim of our, is the aim of solving this equation. Now, to solve this equation, as I said, this is a very complicated equation. So the approach that we shall be taking is a graphical solution. So the curve that you are seeing here, the dark line, the black line, is the left hand side function. So it is, a sine function times a sine hyperbolic function plus a cos function times a cos hyperbolic function. So this is a function of the variable xi, which is dependent, in turn dependent on the energy value E. Okay.
Yes, sir.
Okay. So now, uh, what can we say effectively from this equation? So since we have the cos function on the left hand side, what we can do is, yeah, like I will refer to this graph over here rather than that graph. It's the same one. So, oh no, for now, let me refer to the top one. So see, to solve this, what I have to do is I have to take the cos inverse of the left hand side, correct?
Mm.
Yeah. So you have to take the cosine inverse of the left hand side, then that implies k times a plus b will be cosine inverse of the left hand side. Is that okay?
Yes, sir.
Yeah. But observe the graph. This function is taking a lot of values. Like this is taking all, it's potentially going from infinity to -3 and so on, and it is oscillating. But the cosine inverse function, the cos inverse function, is only defined if the input of that function is between -1 and 1. Like this is the definition of trigonometric functions, because sine theta and cos theta have values only ranging from -1 and 1.
Understand, sir.
Okay, so that is why over here you see that we have marked that there is +1 and then there is -1. Okay, let me see if I have access to these slides. Just give me 1 second. Let me stop presenting for just a second. Yeah, just 1 second. Because I should be having access to the offline copies of these slides. So this is the one. Oops. Yeah. So yeah. So yeah, I seem to have an offline copy of these slides. So okay. So this seems to be a slightly different version, and that's fine. All I need is this graph. So yeah. So as you can see, the point +1 and -1 are present over here. So see, when this function on the left hand side, let me call the left hand side the LHS as f of z. Okay, so only when -1 is less than or equal to f of xi less than or equal to 1, will this equation have allowed solutions? Otherwise, this equation has no solution. Is that clear?
Yes, sir.
Okay. So has solutions. So first we have to find out at what values of xi do I have allowed solutions. So those are these gray regions that you see here. So this is because this point is what? When it is +1, like over here it is +1 and over here it is -1. Similarly over here it is +1, over here it is -1. Only in these regions do I have allowed solutions of k. Is that clear?
Yes, sir.
Okay, so those regions have now been identified. As you can see, region 1 is here, region 2 is here, region, so this is, let me change the color. Yeah, so region, ooh, okay, too thick. Let's see if this is okay. Oh no, this is also, yeah, I'm not used to the pen settings of PowerPoint. Let me just stick to the black one itself. No big deal. So this is region 1 for the solutions. This is region 2, region 3, region 4, region 5, and so on. All right. Now, in this region, now if I give you the value of cos theta. Can you find theta? Kamal or anybody else who's on in the call?
Sir, just you are telling like cos theta.
Yes. So here right now, see, in region 1. So over here, the value of f of xi is what? It is plus 1. Correct? At this point.
Yes, sir.
Okay, so what is the value of cos? So that implies cos times k of a plus b. Sorry, not k of a plus b. Cos times k a plus b is equal to plus 1. So what is the value of the angle? That is what? K times a plus b. What is that? I mean, if cos theta is equal to 1, then what is theta? Like this entire quantity is now theta.
Inverse na sir?
Huh?
Inverse, cos inverse.
Yes, cos inverse 1. So what is cos
Yes.
inverse 1? That's what I'm asking.
Okay.
Pi.
Okay. Is pi the only value or
N pi.
n pi? Where n is equal to what?
Integer.
Integer. Very good. So the allowed values, this implies, so what does this imply? This implies k times a plus b is equal to n pi. But as you can see, the same condition is satisfied at this point in region 2, and this point in region 3, and this point in region 4. Can you see that? Like the same condition, cos k of a plus b is equal to 1 is satisfied, at least in this graph that we can see here. It is satisfied at this point here, this point here, this point here, and this point here. There are 4 points where the same condition is satisfied.
Yes, sir.
So now over here we are supposed to identify that since cos theta equal to 1 has multiple solutions, I can give different solutions to different points. Okay, is that clear?
Yes, sir.
So for the first time when I get this solution, what I do is I will assign the value of n equal to 0. The first time is over here, sorry. Okay. So over here, I will assign this solution for not n equal to 0. That implies what? So let us come down to this graph. So the first time I satisfy cos of k a plus b is equal to 1. The first time that is satisfied, I will say k of a plus b is equal to 0. This implies what? What is the value of k? Come on. This is not that difficult.
0.
Yeah, very good. K is equal to 0. So that is this point over here. Okay. Essentially, see, going up, at this point, we know what the value of xi is. Since we know what the value of xi is, we know what the value of E is. So over here, I am assigning the value k equal to 0. Okay. Now, since I'm assigning the value k equal to 0 at this point, what I will do is I will now draw a new graph that is E versus k, where E is in the y-axis and k is in the x-axis. And the first solution that I've identified is for the value k equal to 0. So at this point, f of xi, or rather, let me say, since we know that xi is e by u naught, I know at this point, at the central point, f of e by u naught is equal to 1. I know this is satisfied. Okay, so similarly, oh, yeah, the same slides. For each value starting from this, I will try to find the cos inverse. And up until this point, I can find the cos inverse. So when I come here, when I come to the -1 point, what happens? What is the value of uh, what is the value of uh, like theta, k times a plus b?
N pi.
For cos theta equal to -1.
Minus.
Yeah,
Okay.
-1. See, I've changed it. Like now from here we have moved down to the next point to -1. Oops, still with the eraser. Yeah, we've come down to -1. So what is k? K times a plus b. So yeah, I mean, in order to save some time, let me give you the answer for that. You can verify it later on. So if this is true, then theta, that is k times a plus b, is equal to 2n plus 1 times pi by 2. Or in other words, it is n pi plus pi by 2. Because, oh, sorry, that is for 0. Uh, wait. I'm sorry, I made a mistake. What have I? 0 plus n pi. Oh, yeah, I'm sorry. We made a mistake collectively. So for the first case, the solution was not n pi. I'm sorry. I should have caught it before itself. Uh, so when cos theta is equal to 1, what are the solutions?
N pi by 2.
No, it's not n pi. It is actually 2 n pi.
2n. Yes.
Okay, yeah. So that was the mistake. I was like, no, at pi by 2 it has to be 0. Yeah. So it is 2 n pi. Okay, it is essentially 2 pi, like integer multiples of 2 pi plus 0. Okay, so it's 2 n pi. And when cos theta is equal to -1, so therefore the allowed values are essentially, 0, 2 pi, and so on and so forth. And the for the points where, similarly for, oops, yeah. So when I say cos times k a plus b, when I call this angle to be theta, is equal to -1, then k is equal to 2n plus 1 times pi. It is essentially 2n pi plus pi. Okay. Is it clear? Yeah, this is
Yes.
correct. I'm sorry, I made a mistake before. Apologies. Okay. So, as you can see, I come down all the way to this point. So, at this point, so let me try to make this slightly more clearer. So, rather than write it here, I will mark. Can I alter the thickness? Oh, yes, I can. Wonderful. So 0.5 mm. Yes. So let me call this 0.1 and let me call this 0.2. So at 1, I have cos of k times a plus b is equal to plus 1. And at point 2, I have what equation? Cos of k times a plus b is equal to minus 1. Is this clear?
Yes, sir.
Okay, so what is the solution that I'm assigning here? Over here, I'm saying k times a plus b is 0. So this is at 1. Okay, so I say k equal to 0. So that is why this is k equal to 0. Similarly, at 2, what do I say? Since this is the first time, as you can see here, this is the first time I'm encountering the solution cos of k times a plus b is equal to minus 1 from the left hand side. This is the first time the minus 1 condition is being satisfied. Therefore, I say that at point 2, cos k times a plus b is equal to minus 1, which implies k times a plus b is equal to pi. Therefore, k is equal to pi by a plus b. And that is what you see here. See? So at point 2, I'm defining the value as value of k as pi by a plus b. Is this clear?
Sir.
Yes.
Yeah, I heard a doubtful. Uh,
Okay, yes, sir.
oh, okay, yes, okay. Yeah, so as you can see, while I'm sharing my slides, unfortunately, I cannot see the call window. So I don't know who's talking. So please bear with that inconvenience. So I just have to, literally listen to the number of voices I'm hearing. So yeah, continuing. So this is that. Now, as you can see, immediately after that, what is the next condition that is being satisfied? The next condition that is being satisfied is the same one. It is cos of k times a plus b is equal to minus 1, which is why immediately after this, for a different value of xi and therefore a different value of e, the same condition is being satisfied. So immediately over here, we once again assign the k value of pi by a plus b. So this is 0.3, that is actually 0.3 on this graph. Okay, so let me get rid of the numbers above to avoid confusion. And in fact, let me write this in red. So first, let me just erase these numbers. Okay, and yeah, so this was 0.1, this was 0.2, and yeah, let me erase this. And this is 0.3. All right, and 0.3 is over here, which is actually for the same k value. But as you can see, this solution occurs at a different value of xi. Since this is occurring at a different value of xi, it is occurring at a different value of E. Therefore, the energy has jumped up. Okay, so here again, from minus 1, we go all the way to plus 1. That is 0.4. So at 0.4, the same equation is satisfied. At 0.4, this equation is satisfied again. But this time, what is the solution we are assigning to it? We are assigning the solution k times a plus b is equal to 2 pi, because that is the next allowed solution. So over here, k is equal to 2 pi by a plus b. And similarly, you can notice that immediately after that solution, there is the next point which occurs at a different value, but for the same equation. That is cos of k times a plus b is equal to plus 1. Therefore, you can see that immediately at the same k value, the next sequence of solutions begin. So I have this as 0.4 and 0.5 is over here. So 0.4 and 0.5. Now you can ask, what about the negative side? The negative side fundamentally comes from the same reasoning that we used for the particle in a box. See, in this equation, the right hand side is given by cos of k times a plus b. And I know that cos theta is equal to cos minus theta. This is a property of the cosine function. The cos function is an even function. Therefore, instead of using the positive value of k, had I used the negative value of k, I would have still ended up with the same equation. Like, because the right hand side will not change if I change the value of k from plus theta to minus theta, like from a positive value to a negative value. Therefore, this graph is symmetrically extended to the negative k values as well. Is that clear?
Understand, sir.
Yes, sir. Yes, sir.
Okay, I hope I've been able to explain this thing like reasonably well.
Yes,
I
sir.
hope like up until this point, I'm just talking about plotting this graph. We have still not come to this graph. I'm not going to discuss this graph right now. We can discuss this later. Like, when we come back to, so as you have noticed, there are a number of topics that we have skipped in between because of this, assignment misalignment. So we have not been able to talk about effective mass. We have not been able to talk about band structure, and we have not been able to talk about the electronic properties based on band structure, conduction band, valence band, and these things. Do not worry, because these concepts will again be coming at later topics. So when we arrive at those topics, I will briefly cover them from the beginning, just like this. So we will spend some time and discuss them then. So right now I have only discussed about the formation of this graph, and I hope that much is clear to you guys now. And I hope whoever sees the recording of this session also benefits from it. All right.
Yes, sir.
Yeah, all right. So with that, I think, any more questions?
Sir, are your recordings are available on your YouTube website?
Yeah, NPTEL should be sharing the links with you.
It's not been shared yet, so that's why I'm
Okay.
asking, sir.
Okay, so I will talk to the coordinators over there. I'll talk to the people at IIT Madras.
Okay,
I'll,
sir.
send them a mail to see what is
So,
happening,
One
because,
question.
huh?
so
Yeah.
can you briefly tell what are the brilliance zones?
Oh, the Brunwa zones. Okay, yeah, let us talk about the Brunwa zones also. Yeah, before that, I heard another question. Like, is there another question?
Yes, sir. Yes, sir. Sir,
Okay.
actually, I'm asking this is for 1D. So all
Yeah.
these graph calculated for 1D. Suppose
Yes.
if I am going for 2D material,
Uh-huh.
though, so the process will be same from KP,
Yes.
blocks, boundary conditions, everything like that.
Yes.
And sir also told like for 2D material, the EK diagram is like 3D.
Yeah.
So everything will be same, na sir? Just
Okay.
mathematical changes. Is there.
So I will address that after talking about Brilwan zones. Okay.
Okay, sir. Okay.
So yeah, I mean, they are connected. The two questions are connected. So see over here now, what do I have? I have a range of k values. Now, what are k values? As we have discussed in the beginning of this session, each k value is a label for an energy state, for an electronic energy state. That is all that the k represents. Yeah, people will like to call it, the momentum, or, they would like to say it is the crystal momentum or things like that. But one need not go into that much details. For all intents and purposes, when I mention a k value, it means it is a particular energy state. That is all. Okay, it is a label. It is enough if you guys understand that. Further things, if you understand, well and good. If you don't understand, it is not a problem. Okay, it is not a problem at all. At least for the intents and purposes of this course. Okay, so when I identify a k value, what is the k value? A k value is an allowed energy state. For reference, over here, so this is for what is the color I'm using? So yeah, so this is for particle in a 1D well. Yeah, I should be using a lower thickness setting. Yeah, right. Yeah, so erase. So this K space that I've defined here is for a, yes, this is much better. Particle in a 1D well. Okay. Whereas in the slides that we have seen, this is the K space for the chronic penny model, the 1D chronic penny model. Okay. So now instead of having a single k value, I have a region, a range of k values from plus pi by a plus b to minus pi times a plus b, or from minus pi times a plus b to plus pi times a plus b. And similarly, I have the second region, that is over here. What is this region? This goes from pi times a plus b to pi by a plus b to 2 pi by a plus b. Is this clear?
Yes, sir.
So
Yes, sir.
similarly, I have the corresponding negative values that goes from minus pi by a plus b to, or rather, let me shade it this way. Yeah, to 2 pi minus 2 pi by a plus b. Okay. So now these different ranges of k values, these are known as the Brillouin zones. So this region from minus pi by a plus b to plus pi by a plus b is known as the first Brillouin zone. These two regions, essentially from minus 2 pi to minus pi, essentially minus 2 pi, like if we are being mathematically specific, comma, it will be this, well, yeah, so let me close them on the left side. So if we are being very, very, mathematically precise, it will be like this. Union pi by a plus b, comma, 2 pi by a plus b. Oh, sorry. So this will be a square brackets. Do you guys know what these different brackets are? Do you know what it means if I put square bracket on one side and curly bracket on the other side?
No, sir.
So do you guys know what open intervals and closed intervals are?
Yes, yes, yes.
So this is that. See, because this point, pi by a plus b is actually common to both zones. So now you can ask, oh my god, so which zone does this point belong to? Oh, actually, I'm supposed to give it to the, yeah. Yes, I cannot make that choice. It is this way. It is not. So, yeah. Actually, it is supposed to be like this. It is supposed to be closed on this side and open on this side. Yeah. So closed on this side, open on this side. So when I put a square bracket, it means the pi by a plus b point actually belongs to zone 2. Okay. In zone 1, I have all allowed values of k until pi by a plus b. But the moment pi by a plus b arrives, I move into zone 2. So the moment 2 pi by a plus b arrives, I move into zone 3. Is that clear?
Yes, sir.
Yeah, so these are the Brillouin zones. The Brillouin zones are simply the allowed ranges of K values for the chronic penny model in this case. Now, the question was asked regarding the 2D material. Okay, so for that, let me quickly, wait. I'm hearing a ping. Someone wants to join? Yes, of course. They're more than welcome. Oh, God. Yeah, switching back. Yes. So, uh, what was I? Where was I? Yes. So, when we are talking about Brillouin zones, we are talking about. You guys can see the screen, right?
Yes, sir.
Yeah. Okay. So, yeah, let me just erase everything here. Okay, I need a bigger eraser. So let me use the top part. So up until now, we have been looking at an equation that is in one dimension. Now tell me this. Are you familiar with a particle in a 2D well? Now, so far, yeah, I would urge you to understand one very important thing. Insofar as the definition of the K space and all these things go, I would readily point this out. See, over here, if you notice, the K values, especially the points, pi by a, 2 pi by a, 3 pi by a, 4 pi by a, is actually very similar to the points that you see here. It is pi by a plus b, 2 pi by a plus b, 3 pi by a plus b, 4 pi by a plus b, and so on and so forth. So can you appreciate that there is some kind of a connection between the particle in a 1D well and the 1D chronic penny model? I hope you can appreciate the connection. Like it is in appearance, there seem to be some kind of a familiarity, because just like I defined the K space there, this is the K space for the chronic penny model. So for each problem, I can define a K space. Okay, so now coming to the 2D solid. So is anyone like Kamal? Did you ask this question for the 2D material?
Yes, sir.
Yeah. So are you familiar with the particle in a 2D box?
No, sir, no.
No. Okay.
Actually,
So,
sir,
uh,
actually currently working in graphene, na? So graphene
uh-huh.
is 2D material. So
Yes, of
that's why I
course.
asked
Okay,
about
so
it.
first I would suggest that you pick up, I'm sure there are, you can find the solution to the particle in a 2D box either on Wikipedia or, some Stack Exchange. There might even be some YouTube tutorials. If you're interested, you can look them up, or any textbook in quantum mechanics will definitely have it. Okay. So
Yes, sir.
essentially what will happen is, remember when we had particle in a 1D box, energy was defined in terms of the variable K. Now, if I have a 2D system, E will be defined in terms of two values of K, Kx and Ky. Because now my material has an x-axis and a y-axis.
Mhm. Yes,
Okay.
sir.
So over
Yes.
here also we could have said it's Kx. But since there is one axis, it doesn't matter. You can call it whatever axis you want, because there is only one position axis. But in two axes, it is standard practice to label them as x and y axis. So since we have x and y axis, E will be of the form kx and ky. So by extension, when you try to solve something like the Chronic Penny model for the 2D system, it is not going to be that easy, mind you. It is going to be very complicated. Ultimately, the equation that you get here, what is this equation of the form? This equation was of the form of f of xi is equal to sum g of k. Correct? Where g of k is cos of k times a plus b, and f of xi is this function. Is that clear? Hello. Am I still around? Oh, oops. Yeah, apologies for the inconvenience. I got disconnected. Uh, can you guys hear me now?
Yes, sir.
Yeah, okay, thank you. Oh, yeah, thanks for the text. Um, so, okay, yeah, so what I was saying before we got interrupted was that when we solve the 1D system, ultimately, in the 1D KP model, to find the allowed energy states, that is the allowed K values, what we have to do is solve an equation of this form. F of xi is equal to G of K. Okay. But in a 2D system, as I just mentioned, there are two values of K. So essentially for a 2D chronic penny model. By the way, there is actually no 2D chronic penny model because there are multiple ways in which you can define a 2D potential that is periodic. So it is slightly more complicated than the 1D case. So the chronic penny model is strictly a 1D model, but let us say hypothetically there exists a 2D chronic penny model. Then in that case, the equation that I have will look like f of xi is equal to g of kx comma ky. Okay. So the function on the right hand side will be a function of both these k values. So when I solve this equation, I will get two solutions. I will get a solution of kx and I will get a solution of ky. So when I'm plotting that solution in a graph like this, my x-axis, which was originally the k value, will now be replaced by a plane. I will have kx and ky. And now the newly defined z-axis will have the allowed e values. So now, instead of having, curves like this, I will have surfaces like this that are defined, that are defined on the 2D plane. Is that clear? Like that is what Professor Vishwendra meant when he said that the graph will be 3D if we are looking at
Yes, sir.
the uh, you know EK diagram for a 2D material.
Clear, sir.
Okay. So, and similarly, the concept of a Brillouin zone and all of these things are extended, of course. And later on in the course, we shall be hopefully seeing a little bit more, but that is the point. This is not a solid state devices course. So, we will not be focusing too much on the Brillouin zones and, even so much so on the band structure. This is a course about the physics of nanoscale devices. So, pretty soon you will see that we will transition to what are known as nanoscopic systems, and we will start discussing about the conduction properties and charge carrier properties of those systems, and our discussion will be primarily confined to that region. However, if there is a need, we will come back and discuss these topics as well. Okay, so this has been a
Sir,
pretty, yeah, any more questions?
yeah, sir. Actually, in future, you can remember this question like that. Suppose in a system where source is there, drain is there, in between a channel is there,
Yeah,
and currently we are working on like nanoscale.
yeah,
So generally the channel is in the nanoscale, but like source and drain are of bulk.
yeah.
So is there any possibility like channel as well as the source drain, all three are in the nanoscale, like that situation?
Ah, okay. That's a good question. So, see, ultimately,
Hmm.
uh, you tell me this. When you build a device
Yes,
or
sir.
anything, anything for that matter of fact, how small can you make it? Like, I'm asking not in terms of electronic devices. I'm asking in terms of devices that you use. Like,
Mm.
I mean, be it a smartphone or some kind of a touchpad or a computer or be it some circuit board that you're using in a car or a bike or a something. How big is it going to be typically?
Like you are directly telling about device, huh? When we fabricate
No,
things.
like
Yeah.
not just electronic devices. Anything that we make, be it
Yes.
hammers, tools, this and that.
At least
Ultimately,
it should be visible, sir.
visibility is not the only criteria. I'm stopping the presentation for a while.
Okay.
See, essentially, what I'm trying to say is, if we have to use something, it has to be something that is tangible to us at some level. We have to control it at in some way or the other. It need
Yes, sir.
not
Yes.
be something that is exactly the size of my hands, but I should be able to control it somehow. Like, yeah, of course I can have a giant aeroplane or a cruise ship that is several hundreds of meters large, that is several hundred meters long, several dozens of meter wide, and maybe 100 meters tall. Now, of course, I cannot move that thing with my hand, but I can create a controlling system that can allow me to drive and manipulate that particular cruise ship or something. So, whenever we build a system, ultimately the question is, what can we control? Okay,
Mhm.
so controllability comes into question. So typically, when you have a nanoscale system, as you will see very soon, what you will understand is, because of quantum fluctuations, controlling that system becomes a very dicey affair. Like,
Okay, sir.
when you reduce a system to a quantum scale, because of especially things like Heisenberg's uncertainty principle, you cannot control that particular quantum system, because at the quantum level, there has to be a certain amount of uncertainty. There will always be a certain amount of uncertainty, and no amount of external force or no amount of energy that you supply to the system is going to reduce that uncertainty or remove that fluctuation. Therefore, when I have a nanoscale system, quantum effects are going to be dominant in that system. But when I have a source and a drain, I want those terminals to be controllable, because ultimately, how do I control the behavior of the device? It is by changing the source voltage, the drain voltage, and the gate voltage. Like, soon we will also see that there is a gate. So those terminals have to be controllable.
Understand, sir.
Okay,
Right.
so if we
Yeah.
take that to the nano zone, we might actually miss out on the controllability. I'm not saying it is impossible, because there is this domain of like, it's not particularly connected with devices per se, but there are areas such as quantum computation where we are talking about quantum bits, where the device is completely a quantum system. So somehow we are sending and receiving information from a quantum system, but the question is, can a quantum bit act as a transistor? Can we treat it as a transistor? The answer is maybe no. Okay.
Mm.
So that is the point. So ultimately, the question you're supposed to ask is, yeah, okay, if a source, drain, and a channel are all nanoscale, are all working in the quantum domain, can I exert the same amount of control? Now you can ask, what do I mean by this control? The control is what we usually see as the current voltage relationships. So can I, in that case, can I define a saturation cutoff and a active region? Can I have an on state and an off state for that device? Can I transition the device from the on state to an off state? Is switching possible? So these are the questions. If I can do that in a device that is completely quantum, then sure, by all means I can have such a device. But as far as my understanding of these things go, if we make everything quantum, then we lose a lot of control. So at the very best, we can use it as some kind of a logical device. We cannot use it as a full on transistor as we see it, because a transistor is more than just a switching device, as you might already know.
Clear, sir. Clear.
Okay.
Go ahead, sir.
Yeah.
Yeah. Thank you
Yeah.
so much, sir.
Yeah. You're welcome. I mean, so we have around 1 more hour left. So yeah, now I think I will go to the week three, walk you through the week three syllabus. Um, what was I thinking? So any more questions from anyone? Uh, Yeah. Nishant, yes, please go ahead. You can unmute yourself and speak. Like, more than welcome. I would enjoy it.
Yes, sir. I have just written that over chat.
Oh, you've written that over the chat. All right. Yeah. Apologies. Week one. Okay. Check it out. As the technology is scaling down, we want to study the effect of transition. Can we apply these concepts on cadence while designing? I'm actually not very familiar with device simulations. So you can maybe post this question on the forum because insofar as I know, there are at least two more teaching assistants here, and I know the other TA here. He has greater familiarity with device simulations. So he will also be visiting the forum. So if you can post this question on the forum, then you will get some response. Even if not from the TA themselves, other students might feel inclined to respond to your question. So I'm sorry. I'm mostly, yeah. So, in case I've not mentioned before, my primary area of research is actually quantum computing and quantum algorithms. So, I am someone who does a lot of mathematics and theory. Since Professor Vishwendra, the instructor of this course, is also my PhD supervisor, I am familiar with the contents of this course, which is why I'm acting as the teaching assistant for this course. I'm not directly working on VLSI or device design or simulation of any kind. So yeah, sorry, it is beyond my scope of knowledge. Apologies.
And sir,
No
Yeah,
problem, sir. Thank you.
yeah. Yes, come on.
yeah, sir, actually, are you aware of like quantum ATK nano lab?
What? I
Like
am.
quantum ATK virtual nano lab.
No, I'm not. So
Okay,
is
okay.
that some kind of a platform where we can
Yeah,
design
nano level
quantum
simulation, sir.
devices? Okay,
Yes,
okay.
sir. Right,
Yeah,
sir.
again, as I said, my primary focus is on quantum algorithms. So I do computer science and like the mathematical aspects of quantum computing. I'm
Understand, sir.
I'm
Yeah.
familiar with devices. I have some rudimentary understanding, but that is not a part of my PhD work. So I don't spend too much time on those things. So again, if it comes to doing any kind of device simulations, can I do it? Maybe if I practice for some time, but am I doing it? No.
Okay, sir.
Okay, yeah. So let us carry on. Let us start with this week's session, or rather, the week three content. I mean, the week's discussion session has been going on, and I'm happy that I've been able to spend over an hour on questions that you guys have. I'm glad that I'm able to do that, and I prefer that we can, continue working along those lines. So, yeah, right. So, yeah, before that, let's, I have like two or three slides prepared. So let's, quickly look at that. So I hope you guys have seen the lectures for week three because the assignment is due in another 4 weeks. Sorry, 4 days. Apologies. 4 days. So these are the topics that have been covered in week three. The lectures that are present in the week three module. So primarily, week three is dedicated to the discussion of density of states. So the lectures should have, covered the concept and definition of density of states, and then bulk of the lectures, around three or four of them, should be dedicated to deriving the electronic density of states in solids. So there are certain assumptions that are involved in that, and then the lectures will contain the derivation for the 1D, 2D, and 3D solids, the density of states expression, and
Sir,
yes.
are you showing slides right now?
Oh, okay. You guys, I forgot to share the screen. I'm sorry.
Yeah.
Yeah. Again, like the moment I, fumble something like this, please stop me right away. Yeah. A window. So this is three. Now, can you see it? Can you guys see
Yes,
the
sir.
slides?
Yes, sir.
Yeah. Good. So yeah. So these are the topics covered. As I was saying, primary content for this week is density of states. So Bulk of the discussions must have been centered around, not must have been, are centered around deriving the density of states expressions for 1D, 2D, and 3D solids. And so the derivations are presented in detail in your lectures. I suggest that you go through them. I hope you have at least seen them already. Like, this is for both the people who are attending this session right now and the people who might see the recording at a later date. So kindly go through the derivations. I shall be talking about the derivation in my own way briefly. And the last part of this week's content should have been focused on Fermi Dirac statistics, which is the statistics followed by electrons, by particles that are like electrons, which are referred to as fermions. So, in that, you should have seen the form of the Fermi distribution function, certain properties of the Fermi function, and the concept of this quantity known as the Fermi level. So these are the topics that have been covered. So in whatever time is left, what we shall do today is essentially try to do an alternate derivation of the 1D density of states, and thereby try to give you a slightly different definition of the idea of density of states, and the energy dependence and so on and so forth, because these will be the questions that you will have in the assignment for this week. And after that, we shall work out some problems which shall help us in understanding the property of the Fermi Dirac distribution function. Okay, so these are the two topics that we shall be covering today as a part of our session. So, with that, let us get started. Uh, let me change my so why can't I just switch a window? Okay, Nishant seems to have dropped out. Now we'll see if we can join us again. Okay, he will come later post completing week 3. Cool. Up to him. Yeah, so window. Okay. Guess I have to share my entire screen. Yeah. So can you guys see the whiteboard? Hello, can someone please confirm that you can see the whiteboard? Kamal, anyone? Can you please confirm that you can see the board? Hello, am I audible? Can you guys hear me? Okay, that was the connection. Oops. Yeah. Can you guys hear me?
Yes, sir.
Okay, yeah.
Yes,
So
sir.
there seems to be some issue with the Wi-Fi here today. Yeah, apologies for the network difficulties. So yes, resuming. Yeah, can you guys see the board?
Yes. Yes,
Yeah,
sir.
good. Thank you. So yeah, as mentioned, we shall start today's discussion with the idea of states. So insofar as symbols go, density of states for our discussions, and I think even in the class, the lectures, it will be denoted by this function g of e. Okay, now what is the definition? So g of e is defined as the number of states between energies E and E plus dE. So technically speaking, G of E, as the name suggests, is a density function. So strictly speaking, this quantity is defined as G of E times dE. So if I have to define number of states between energy values E1 and E2, where let me assume that E1 is less than E2, then that is given by integral E1 to E2 G of E dE. So are you guys okay up to this point? Any questions?
Okay, sir.
No
Okay, sir.
questions, right? Yeah, okay. Yeah. So this is how the quantity is defined as. So essentially, the density of states essentially tells me that for a given system, it will tell me how many energy states are available between two energy values E1 and E2. Here it is assumed that energy E1 is less than E2. Okay. So, and of course, like by direct definition, the density of states function g of E is a function of the energy of the particle. So this is the basic idea, the concept, and the definition. Now, how to derive the density of states? So there are. So let me just switch colors. So when one talks about derivation, okay, that doesn't look neat. So when one talks about derivation, there are two approaches. I mean, there are several approaches, but there are two approaches that I can think of. So approach one is essentially using the k-space. So this is what you would have seen in the last lecture of week 2 and the week 3 lectures. So essentially the k-space for a 1D, 2D, 3D system will be defined, and then you will try to find the volume occupied by a single state in the k-space, and then the derivation follows a lot of steps. Have either of you guys seen those derivations? Can I get a response?
So today we'll start week 3.
Okay, today you will start with week 3. Okay, wonderful. So this is covered in lectures. So please go through the lectures. I'm not going to repeat that because you already have hours of content on that. Now, approach 2 is what I will call the direct counting approach. Now, the direct counting approach is difficult for 2D and 3D systems. But it is actually pretty easy for a 1D system. Okay, so let us see how to do that. Yeah. So, okay. Since you guys have not seen the week 3 content, let me quickly talk about some of the assumptions. So, the discussions in week 3 are pertaining to solids. So, what can we say about solids? I'm asking you guys, like, what properties can you tell me about solids? Think, like class 5, class 6, when you learned about states of matter for the first time.
Crystal structure.
Okay, crystal structure, that is actually significantly higher level. Something more basic than crystal structure. Okay, solids of course have crystal structure.
They are quite hard.
Okay, hard.
Hard
That
surface.
is okay. That is slightly more something more advanced than hard, and less advanced than crystal structure.
Okay, sir.
So see, one thing
Having
that
no,
huh?
like having no empty space.
Very good, very good. Yeah, that is definitely one thing. Like they have a very high density. So along with that, what we know is a solid usually has definite dimensions.
Mass also. Solids have definite
Like
mass.
liquids also have definite mass, gases also have definite mass. But what I'm trying to say is, if I take a piece of solid and say it is of length, say 2 centimeter by 3 centimeter by 3 centimeter, then outside of that region there is no solid. Do you understand? Like I don't have to contain a solid using another device or another object. A solid is self-contained. Is that clear?
Yes,
Like
sir.
it is self-containing. Whereas if I have a liquid or a gas, I need a container. Does that make sense?
Yes, sir.
Like if I have water, of course, like even if I don't have a container, the water will be there, but I will no longer be able to use it. So if I want to use water, then I will at least need a bottle. I will need some kind of a container in which I need to store the water to use it for some purpose that I want to. But if I have a solid object, I don't have to put a solid object in a container unless and until I want to protect it from external impact or something like that. Other than that, be it a hard solid or a soft solid or whatever, a solid has definite dimensions and it is self-contained. Now this can sound like a very trivial thing, but this is very important in the next step that we are going to take. So what does this imply? If I have electrons in a solid, where are they? Like if I say I have my solid material contains electrons, then what can I say about them?
They are fixed.
Not fixed, they're definitely in the same region as the solid. Do you
Yes.
understand?
Yes, sir.
So, if I have a solid that is, like this, of a certain shape. For now, let us assume that, it is some, uh, um, some length, some breadth, and some height. Okay, this is a solid. Let me call it. that, then the electrons in the solid are confined in this region. Like that is a very good assumption to make. So then, what kind of an environment are the electrons in a solid present in? This is a 3D solid. So what is now we know that electrons actually move freely. Like this is something we have known through studies that electrons present inside the solid can actually move. The nuclei are fixed, but the electrons they can move around. At least some of the electrons can move around. So what is the environment in which these electrons are moving around? So can I call it a 3D box? If I call it a 3D box, am I correct?
Yes, sir.
So that is the point. So essentially, the electrons should stay in this region. They should stay strictly in this region. Like they cannot jump out of it. Unless and until I give some external energy or I do something to those electrons, they should not jump out. Because charge neutrality is a thing. The positive charge of the nucleus will attract the electrons. So because of that effective force from multiple nuclei and inter-electron interaction and all such things, the electrons in a solid are by and large confined within the solid. So they are present in a 3D box. So let us say instead of a 3D solid, I have a 1D solid. Okay. Now, what about electrons in a 1D solid? What is an easy way of describing electrons in a 1D solid?
But they are confined in one direction, like that.
Yes. Therefore, what is that system? They are electrons in. Oops. Electrons in a what? In a 1D box.
Yes, sir.
Okay. Because see, in a 3D solid, the electrons are confined in a 3D box. Okay. So in a 1D solid, are electrons in a 1D box. Now, do we know how to study the quantum mechanical properties of a 1D box? Um, Kamal, at least you should be able to answer this question.
We studied, na, sir.
Yes.
Yes.
So, can you tell me what the energy of an electron in a 1D box will look like? E is equal to what? Let us say the 1D box has a
A
length
sin kx.
L. No, I'm asking the energy. Do you understand?
It is constant. Energy will be constant.
Energy is constant.
No, in a 1D box.
Yes. Okay. In a 1D box, are the energies continuous or are they discrete?
Energy is discrete, sir.
Okay, so what are the discrete values?
Energy states.
Yes, energy states. Is this correct?
Right, sir. Right.
Right.
If formula forget. That's why.
That is all right. That is all right. But please don't forget it for long, because these formulae might be useful in your examinations and all. So these are
Yes, sir.
slightly important. So please try to
Understood.
remember these things.
Yes.
Okay. Like
Sir.
again, these discussion sessions do not carry any marks. Attendance is not compulsory. You give wrong answers, you give right answers, it doesn't matter. But please do remember the things that are discussed here, and the things that are covered in the class. This has been done throughout week 1 and also partly in week 2. So this thing you should remember. So
Yes,
now
sir.
n is of this form. Sorry, e is of this form, and n can take value 1, 2, 3, so on and so forth. Okay. Now tell me this. If I say give you an energy value E naught, okay, how will you find the value of n corresponding to E naught? My question is, if E naught is given, what is n? How to do this?
You can use that above formula.
Yes. So can you tell me what the expression for n is?
E into 2 ml square by pi square h cross square root over.
Okay, very good. So E into 2ml squared divided by pi squared h squared under root, which can be written as whole bar half. Correct? Is this correct? Hello. Yeah, can you guys hear me?
Yes, the voice is clear. Yes, sir.
Yeah, so is this expression correct?
For me, it is correct, sir.
Yeah, so yeah, I'm asking only for you. I mean, you cannot answer for everyone. If you think it is correct, please say it is correct.
It's correct.
Yeah, okay, good. So this is good. So this is n. Ah, now I'm going to ask a slightly different question. And that question is this. Now this is n. Now the question is how, oh, and by the way, this is not just E, the given value of energy was E naught. So this is E naught. Yeah. How many states exist with energy E less than or equal to E naught? So this is the question. Is the question clear? Oops. Yeah. Is this question clear? Hello.
So, yes, sir.
Yeah. So is the question clear? Or
Yes,
do
sir.
you have any doubts with the question itself? If you have, please ask. Don't try to answer the question yet. I'm just asking, is the question clear? I mean, we shall be discussing what the answer is. This is not an assignment question. This is a discussion question. Yeah, so Kamal and Lakshmikant are both here. So,
Sir, can
yeah,
you give this question in a graphical pattern like?
no graphical pattern. I'm just
Okay.
asking,
Hmm.
like, that is the thing. You don't have to think about the answer. We shall be discussing what the answer is. What I'm simply asking you is, have you understood this question?
Sir, E is okay, where E not
Uh-huh.
question like that in the base it's written like zero.
Yeah,
So
yeah.
from
Oh, acha, acha. See, that E naught is the same as this. E naught is just a symbol, it's a constant value. See, when I write this expression, E is a variable here, correct?
yes, sir.
When I change N, I get a different value of E. Here, I want to say that E is a constant. Therefore, I write it as E naught. That is all. It is just a symbol.
Okay.
It is not some special number. It is just a symbol. It is a constant. If I give you that constant, you can find the value of N using this formula. Up until that, it is clear.
Yes, sir.
You can find N. Now, my question is, how many states exist with energy E less than E naught? If I give you a value of E naught, can we find out how many states exist with energy less than that?
Yes,
Yes.
sir. Calculate.
How? Very good. I mean, both of you said yes. So, can you tell me how?
Okay. So in the formula of n,
Yes.
where E naught is there, we'll put E naught value, and from that we
Yes.
calculate the value of n. And in the
Yes.
formula of E, we will put the value of n and calculate the E value, capital E value.
No, like then I will get back E naught.
Okay.
वो तो reverse हो गया ना, like I mean that just becomes the opposite, but you're close. Yes, so if I find out N, now how many states exist with energy less than E naught or E naught? let us say
Yes, sir.
let us say you solve this equation and find out that N equal to 3. Let us say, okay, now tell me how many states exist with energy less than or equal to E naught.
So it will be 2, sir.
Less than or equal to?
Uh, Less than.
No, I'm asking less than or equal to. My question is less than or equal to, not less than.
It will, okay.
Then it will be 3. You're there. Because n equal
Yes,
to
yes.
3, then
Yes, less
what
than
are the
equal
other
to.
states that have energy less than or equal to this? It is n equal to 1, 2, and 3.
Yes, sir.
Okay, that's all. Is this Kamal? Did you
Okay.
get this?
And yes, sir.
So
Right.
that is all. It is just numbers. We are just counting.
Mm.
Okay. So if I solve this expression and I find that there is an n, okay. So now can we make this slightly numerical? Shall we make this numerical? Okay, let us make this numerical. So now, uh, yes. So you know what? Okay. So I have a suggestion to you guys. At least Kamal and I mean this is to also the people who are listening. If you are attending the live session, I humbly request you to at least view the lectures of the upcoming assignment, because sure we will spend as much time as required in getting your doubts cleared, but I would also like to discuss something that would benefit in you guys solving the upcoming assignment. So since you guys have not seen the lectures, I cannot just assume that you know those things and go ahead and teach them because you've not seen them. So that would be like too much effort for you guys also. Like I cannot expect you guys to understand a week's worth of content in a 1 hour discussion. Okay. So next week onwards, if possible, at least go through the slides, if not the lecture videos themselves. At least go through the lecture slides for the upcoming assignment, so that we can have some discussion for the upcoming assignment also. Of course, we will spend as much time is required in getting the doubts cleared. Is that okay, Kamal and
Yes, sir.
Yes,
Lakshmikant?
sir. Yes, sir.
Okay. Yeah. By the way, Lakshmikant, is your name Lakshmikant or do I have to pronounce? Is it Lakshmikant?
So it's okay, sir. You can pronounce
Okay,
Lakshmikant.
it is Lakshmikant, right?
Yes, sir.
There is
Yes.
it's not Lakshmikant.
No,
Okay, fine, fine, fine. No, I was wondering if you made a typo with your name because I have
no,
in the
sir.
past.
Actually, it's my name, sir.
Okay, okay, okay. So Lakshmikant, okay, yeah. So Lakshmikant and Kamal, in case you guys show up next week, please see if you can, at least go through the lecture slides. Okay. So today I'm not going to do the discussions again on the Fermi Dirac functions because it doesn't make sense. If you guys have not read it, I cannot, just um, solve problems without context because a
Yes,
that
sir.
will be difficult for me and b we only have 15 minutes left. We have spent most of today's discussion on KP model, which is a good thing because other people who have a doubt in this derivation, and I'm sure a lot of people do have that, can see this recording and benefit from that. But going forward, we will try to incorporate as much of the upcoming week's content also as possible. Okay. So all right, so continuing. So in this case, yes, if I can find the value of n, then things are good. So now let us say, now let us, make this whole affair numerical. So what shall we do is, no, let me open this thing itself. Open up. So this quantity, other than n square, this entire quantity, let me say this is equal to 10 electron volts. Is that clear? Like, have you guys understood?
Yes, yes, yes.
Okay. So this is 10 electron volts, which implies E is equal to what? It is equal to 10 times n square electron volts. Correct? Is this okay?
Yes, sir.
Okay, good. So now the following question that we are going to questions we are going to solve is based on this formula. Remember this. So, yes. So, as I was saying, E is equal to 10 into n squared electron volts. Now, first, question one. If E dot is equal to 160 EV, what is the value of N? Do you have an answer?
Four.
Very good. So how do we solve it? Essentially, N is equal to E by 10 whole power half under root. Okay.
Mm.
E divided by 10. So let me again, let us try to make it as unambiguous as possible. E divided by 10 power half. Okay, so that is 16 by 10 power half. Okay, and that is equal to 4. Very good. So now, how many energy states exist with E less than E naught? Less than equal to E
One,
naught?
two, three, four.
1, 2, 3, 4. So there are 4 energy states. Clear?
Yes, sir.
Okay, so now I am going to ask a slightly different question. How many states have energy less than or equal to 100 electron volts? How do we find this?
For E equal to 10 n square electron volt, na sir?
This is the formula E, yes. But here I'm asking, yeah, with energy less than or equal to 100 electron volts.
Only one energy state?
Uh,
Wait, sir. Sorry.
yeah, no worries, no worries, no worries. Take your time. We still have around 15 minutes left for the session to end. So, I mean, we are just going to be discussing this problem and, we're going to be doing a little bit more than this. Yeah. Okay. Like you guys continue doing it. In the meantime, I will also pick up the solution. So first, I want to find out what the value of n corresponding to this energy is, if it at all exists. So I will say n is equal to same formula, 100 EV divided by 10 whole per half. So that is equal to what? Square root of 10. What is square root of 10? Square root of 10 is 3.16 something something, correct? Approximately, right?
Yes, sir.
Okay. So what does this mean? This means, see here, what should be remembered is n is equal to 1, 2, 3, and so on. Okay. That implies the energy levels, if we are drawing it as a graph, are what? Are 10 EV. And after that, what is the second energy level? Can you tell me what this is? Like, Kamal, did you ask for a graphical solution? So yeah, can you help me finish this graph? What will be the second energy level? Hello. Am I still in the call? Can you
Yes,
guys
yes,
hear
sir.
me? Yeah, yeah.
Yes.
So yeah, so forget the previous question that I asked. Just this, like these are the energy levels. So first is 10 and 10 EV. What is the second energy level? Come on, it's not that difficult. Oops. Yeah, it's not that difficult. Come on,
20.
20. What is the formula here? Jesus. Yeah, Once you get a straight line, it's hard to do it again.
So energy first is 10, 1. Then second
Yes.
is 2. The 10 into 2 square, 10 into
Yeah.
4,
Yeah. So what is that?
40.
Yeah. So tell me 40.
Then again 3 square,
Yes.
90.
Good. That's all I was asking. Yes. Well done. So 90. What is the fourth one? What is the fourth energy?
160,
Fifth?
250.
250. Wonderful. So, essentially, what we are supposed to remember here is the spacing between the energy levels, like it should increase. So, yeah, so that's what I'm trying to capture here. But unfortunately, like, I mean, I'm pretty bad at drawing on simple paper or even blackboard. So, drawing with this thing, touchscreen is like, it's torture for me. But yeah, I'm trying to do something meaningful, coherent. So this is 10. So roughly 4 times this. So it's going to be somewhere over here maybe. And the second one is almost twice this. So I take this and it's going to be somewhere up here. And the let us do up to the fourth energy level. The fourth energy level is, well, it's not quite double of this, so it's going to be all the way up here. It's going to be somewhere over here. Okay, so this is going to be 10 eV. Okay, this is going to be 40 eV. And this is going to be 90 electron volts. And this is going to be 160 electron volts. Okay, now what was the question that I was asked? How many states have energy less than or equal to 100 electron volts? Where does 100 electron volts lie here? Somewhere over here, correct?
Yes, sir.
So how many states lie below that?
3.
Brilliant. So that is what I'm seeing here. So whatever number I see here, what am I supposed to do? I'm just supposed to take the integer part of it. Is that clear?
Yes, sir. Yes.
So I get 3.16 here. I just take the integer part of it. So that implies number of states less than or equal to is 3. Okay. Is that fine? Is that clear?
Yes, sir.
Yes, sir.
Okay, that is clear. Wonderful. So now this quantity, do you know of a function or a mathematical operation that allows me to find the integer part of a number? Just out of curiosity, I'm asking. Are you familiar with functions called the greatest integer function and the lowest integer function?
Yes, sir.
So what function would you use to get 3 from 3.16?
Greatest integer function.
Yes. So greatest integer function is greatest integer less than or equal to the given number. Lowest integer function is lowest integer less than, greatest integer is, largest integer less than or equal to, lowest integer is smallest integer greater than or equal to. So you are supposed to do greatest integer. For those familiar with, computer science notation, that is known as the floor function. It is the floor of this number. Okay. However, we don't care about that. Essentially, what we are trying to understand is how does this quantity, number of energy states, vary with the given energy. Okay. So, essentially, so whatever number I get here is kind of the answer. If I get 4 here, the answer is 4. If I get 3.16 here, the answer is 3. Is that clear?
Yes,
Yes,
sir.
sir.
Okay, so the point is, now tell me this. If the particles are electrons, then how many states will I have? These are energy levels now. If the particles are electrons, will the number of states change? Will something change? Can you see what I'm doing?
Adding a
Spin,
spin.
spin
Yes.
off.
So how will this number change?
There will be no
Electrons have a
change.
spin. Huh?
There will be no change.
No, but how many electronic states are available now?
2.
Yes. So for each state, there are 2 electronic energy states. So now the answer is not just 3, it is 3 into 2. It is 6. Is that clear?
Okay.
Like essentially, how many electrons can exist with energy less than or equal to 100 volts? 2 electrons with 10 eV, 2 electrons with 40 eV, and 2 electrons with 90 eV. So 6 electrons can exist. Is that clear? Can you guys understand that? Because we are
Right.
talking about electrons. Hello.
Yes, sir.
Yeah, so is that part clear?
Yes, sir.
Yeah. So now let me define this function. Whatever. So the number of electronic states with energy E less than or equal to E naught is given by what? It is given by, so let me call this function n of E. N of E is 2 times this number n that we had previously defined. So what is the formula for n in general, not for just this formula, in general, like when I consider a particle in a 1D box. That is this. That is this over here. Correct? Can you see this?
Yes, sir.
Yeah. So, but since we are looking at electrons, we will have twice that number. So, n of E naught is equal to what? It is equal to 2 into E naught times 2m L squared divided by pi squared h bar squared whole power half. Is this clear? Is this okay?
Yes, sir.
Yes, sir.
Huh? Up until this point, this is fine, right? So this is n of E naught. How we have done it? We have done it by simply drawing this graph. Of course, when I get an answer that is not an integer, what I'm supposed to do? I'm just supposed to get rid of the decimal part. That part also we have understood. So whatever value of E naught I substitute here, we will get an answer. We know how to get an answer. Now, finally, to conclude today's discussion, let me just derive the density of states. So for a 1D system, for a 1D solid, So G is how we denote the 1D state, and typically we put 1D, 2D, or 3D below that as a subscript to denote how many dimensions we are talking about. So G1D of E is D, oops, uh, yeah, is D by DE of N of E. Okay, where N of E is as defined in the previous slide. So what is N of E? N of E is equal to 2 into E into 2mL squared by pi squared h bar squared whole bar half. Now there are a lot of square terms here. Let us pull all of that out. Oh, yeah. There is also one more thing. So it is actually not just d by de, it is 1 by L into d by de. Yeah. So the quantity you will have here is like pulling out all the terms that are square out of that. I have 2L by pi h bar into square root of 2me. This is n of e. Okay. Now, can you find out what 1 by L into d by de of n of e is? Can you do this? Can you take the derivative of this function and then divide by L? Can you guys hear me?
Yes, sir.
Yeah, so can you do what I just showed you? Can you take the derivative with respect to E and then divide by L?
Yes, sir.
Yeah, so what will the answer be? Can you tell me quickly?
Root over of
Uh-huh.
me
Root over of
by me
ME.
to
Okay.
me
To ME. Okay.
by
Uh-huh.
pi h cross.
What about the derivative part? You haven't taken the derivative.
Okay, sir. Oh, yes, yes, yes. Sorry, sir.
No, no issues, no issues. Take it up. So yeah, the function here is square root of E. Taking the derivative of that, we know that. Like over here, we know that d by d of e to the power half is 1 by 2 root e.
1 by 2 root e.
Yeah, so since we know that that is 1 by 2 root e, what we will do is when we take the derivative, we'll essentially have 1 by L into square root of 2m by pi h bar into 1 by 2 root E. Okay, and of course there is also a 2L
2
into, so
into 2.
2 into L divided by L into
Can
this quantity. So the L and L cancels out, the 2 and 2 cancels out, and this is 2 square root of E. Okay, yeah, let me make it slightly neater. So 2 square root of E, and over here it is, yeah. So this cancels out, and this two cancels out. So ultimately what we are left with is 1 upon pi h bar into square root of 2m by e. Now this formula by our definition is equal to G 1D of E. This is the 1D density of states. Now since you guys have not gone through the lectures, what I will do is simply show you the result from the slides for week 3. So if we come all the way down to, yeah, 1D material. Yes. So you'll see that there is a derivation present in the lectures here. Yeah. So as you can see, yes, there is another factor of 2 here which kind of appears for a different reason. But ultimately, you can see that the formula here is what? 1 by h bar pi m by 2e, and we get a similar expression over here up to a factor of 2. Now that factor of 2 is something slightly different. You shall see why that is so during the lectures. So can you see that this expression is similar to that expression?
yes, sir.
Yeah. So this is one way of deriving the density of state for materials. But however, this method that we have discussed so far is only easy for 0 and 1D systems. I did not discuss 0D systems because I mean the energy distribution of 0D systems has not been it would be better if you guys go through the lectures before that. So with this, we will stop today's discussion. So as you can see, we have done at least the derivation of one form of density of states. So I will stop my presentation with this. Why am I opening that again? Yeah, stop sharing. Yeah. So, okay, Kamal seems to have dropped out of the call. No issues. The session is over either ways. So, that is the thing. So, today's discussion has primarily been about the chronic penny model and Brillouin zones. So, we have spent a good amount of time clarifying certain issues regarding that. Um, After that, we have briefly spent some time talking about energy distributions and trying to count the number of states above or below a given energy level. So based on that, we have tried to develop a notion of density of states, and we have done a preliminary derivation that kind of allows us to derive an expression for the density of states. So up until that is will be available in this session as a part of the slides and the recordings. So I hope this would augment your reading of the content of week 3, and I hope parts of it also helps you with the solution of the assignments. Once again, if you have any further doubts or queries, please feel free to post them on the forums, and we'll address them as and when they come up. And small piece of advice for people who are intending to attend these sessions. I plan on covering certain problems that are helpful for attempting the upcoming assignments. But for that, it would be helpful if some members are present who are familiar with the upcoming assignments lecture contents. So for people who are currently present in the session and people who intend to join the session in the upcoming weeks, I would appreciate it if you guys can at least view the lecture slides for the ongoing week, so that we can have certain fruitful discussions on the upcoming assignment as well. However, if you have any queries with the previous assignment or the previous contents covered, I will be more than happy to address them. So I thank you all for attending this week's session. and for staying online. So that is all for today. We will meet again um, next week, same time. So I'm ending the call. Once again, thank you for attending. Bye.